thesis mainly is about the what they look like in the complex plane, but I'm going to show you what they look like in XY space first, just to give you like a geometric interpretation. So, and to describe the real points on the curve for curve C, so that so this is just a general notation. For some field, the points on a curve C are just C from C to field. So the equation of an elliptic curve in the xy plane is this: y squared. Y squared equals ax cubed plus bx squared. And there's some condition here. A is not 0, otherwise it's not cubic. And if we let this guy, this right-hand side, be f of x, then f of x has the same roots. Okay, now, what do these look like in XY space? They're pretty nice looking, and there's two different ways, there are two different kind of graphs they have. And one of them looks like this. They have, see this? This is if f of x has one real root, that it only intercepts the x-axis at one point. You get this kind of sideways horseshoe looking graph. And if f of x has three distinct real roots, then it looks like kind of this egg thing on the left-hand side, and then there's this other part. Okay, so just that's briefly kind of an introductory thing, what they look like in particular. And now I'm going to show you how this equation relates to the complex structure, and I'm going to start talking about something that sounds like it has nothing to do with this at all, but there's a really nice differential equation that brings it all together here. So, I got to talk about what the lattice in the complex structure is. Okay. So, alright, given omega 1 and omega 2 that are complex numbers such that omega 1 and omega 2 are linearly independent over R. We define the lattice for omega 1 and omega 2 as follows. The lattice L is a set of all n omega 1 plus m omega 2, such that n and m are integers. So, and we can just shorthand notation, right? This wherever I can. So the way you want to think about the lattice is that you're given these two complex numbers, omega 1 and omega 2, and there's no real number such that omega times a real number is equal to omega 1 times a real number is equal to omega 2. And the lattice is all integer linear combinations of these two vectors. So what does this look like in the complex plane? Well, it's a discrete subset. It's actually an additive subgroup. But so you're given, call this guy omega 1 and this guy omega 2. The lattice looks exactly kind of what you would expect it to look like. There's like this point, which is omega 1 and omega 2. And then this kind of discrete subset of the complex plane that extends to infinity. So we have like these points. One down here. And so the lattice is all of these points of the complex plane that are of that form. but how we want to relate this to elliptic curves is we want to look at the quotient subgroup. We want to mod C out of the lattice. Well, what does this look like? Well, C mod the lattice is a quotient subgroup, and I want to try to describe it by saying it's analogous to something like Z mod 4Z, which is 0, 1, 2, 3. But I mean, the elements of Z mod 4Z aren't really 0, 1, 2, 3. They're like these, they're the cosets. They're all the equivalence classes of 0, 1, 2, and 3 mod 4. And that's how you want to think of C mod the lattice. So you mod out by the lattice, and you get like this truncated version of the complex plane. You shrink it down into the like, we call this the fundamental period parallelism. So you, like, for some Z naught in this parallelogram, what you're really saying when it's an element of C mod the lattice is this complex number plus, you know, all elements of the lattice. So this, we want to think of elements of C mod the lattice as points in this parallelogram, but really they're cosets. Okay. Now, the big theorem is that C mod the lattice is isomorphic to the complex points on the curve C. I'll show you why, and I'll show you what this curve actually is. So if we call this mapping, let's say P goes from C mod L to the complex point on the curve, where we take V of Z, where Z is one of these guys in the complex plane, and we send that to V of Z equals this function called the Weierstrass P function, and then its derivative. So we're taking the point in the complex plane, and we're sending it via this function, which I'm about to show you, to an ordered pair. You evaluate this function at Z, and then you evaluate it at, you evaluate P at Z, and you evaluate P prime at Z, and I'll give you an ordered pair on the curve. And the P function is an infinite series, and it looks like this. The P function is an infinite series, but it's also based on like a given lattice L. So for any lattice, there's an associated P function. And just to show you that it depends on L, I'm going to write semicolon L, but it's just a function of C. And that equals 1 over Z squared plus the sum of all omegas in this lattice L, except for 0, of this thing. Z minus omega squared plus 1 over omega squared. So, I have this pretty crazy looking P function that sends complex points to points on the curve. And then you can prove that this map is 1-to-1 and onto, and it's a homomorphism. So it's an isomorphism. So these are basically the same group. The operation here is like regular addition of complex numbers, and the operation here is kind of a funky kind of addition on the curve. You can kind of understand it in your mind. But it's really complicated, and if I were to prove it with a group, it would take a long time. But what's this curve that you're sending it to? We have this map, and we know it goes, well, I'm telling you it goes to some curve, but we want to actually write down what that curve is. So what is, well, the P function is nice because it satisfies the following differential equation. Okay, so for any P function, we know that the following differential equation. So P prime of P squared for E of z q minus this constant g2 of L, which is a property of the lattice, times E of z minus g3 of L. The g2 and g3 are the following numbers. g2 of L, g2 of L is 60 times the sum of all the elements of the lattice, or over all the elements of the lattice of 1 over omega. G3 is similar. It's 140 times omega, sum of all over omega in the lattice, 1 over omega. So, given some lattice and d2 and d3 of that lattice and the p function, we write down this differential equation. But if we substitute x for p of z and y for p prime of z, then we get this equation in y. I'm just going to write d2. Okay, so this mapping sends a complex number to this ordered pair that satisfies this differential equation. And if we take this ordered pair, p of z and p prime of z, and we substitute x for p of z and y for p prime of z, then it satisfies this equation. But this is an elliptic curve based on this equation over here. B is 0, and C is negative G2, and D is negative G3. So that's how you get from the complex plane this lattice structure, this thing that looks like it has nothing to do with these pretty nice equations in R2, to an actual formula for the curve. Of course, the p function can take on complex values, but you can let x and y be complex, and this still holds. So, I mean, it's possible that it doesn't, I mean, that, yeah, because it maps to the complex point of the curve. This is just part C, that's just the real point. Okay, so that's kind of like the background. What I'm doing for my thesis is, well, right now, is my problem is that given a lattice L, how do we find the equation f of x, or y squared equals f of x? And I'll show you how. For some really nice lattices, it's so there are some really nice lattices for which this is not too difficult using mathematics, and I'll show you how. Okay, so I have some lattice L. So given L and omega 2, how do we find Now, there is a way to do this. It's that exists already, and it's this mathematician Weber. I don't know exactly when he lived.
19th century.
19th century. Was it like late 19th century? Yeah. Okay. I didn't want to. He has these Weber functions, and but they're really complicated, and it was before we had Mathematica, which makes things a lot easier. So he couldn't do it, but I can. So there's a theorem in a book by a guy named David Cox, and it says that, well, first I want to preface it by talking about principal ideals, which are, lattices, some lattices, there are 13 of them actually, and they're especially nice because they're rings, but they also have this property that every ideal is principal. Now, what is that? Well, okay. So given a ring R and the ideal U is a subring such that for any element of the lattice, of the ring, and for any element of the ideal, that R times U is in U. So U is a subring, so it's closed within by addition and multiplication, but it's closed from outside by multiplication as well. So you multiply anything in the ideal by anything in the ring, and you get something that's still in the ideal. Like the analogous structure in group theory would be a normal subgroup. That's an easier way to think of it, I suppose. So what does it mean to say that every ideal is principal? One idea, a principal ideal. So principal. Generated by some element of itself, just like a cyclic subgroup of a group is generated by some element of a group. Okay, what is this generated by? So it's all multiples of some element of itself. Now, some of these lattices have this property, and it also means they have some other really nice stuff going on that I'm about to tell you. So, 13 lattices of 1, alpha, where this is omega 1. Omega 1 is just 1, and omega 2 is just alpha. Have this property that every ideal is principal. You also can call this a principal ideal domain, and I'll just abbreviate that PID. PID. So, and for those that are, for those lattices, there are two different ways to write their P function, and by writing their P function in these two different ways, we can find the equation for the curve in terms of x. Okay, so for those lattices, it's true that P of alpha times D, where alpha is omega 2, is equal to this two polynomials, the quotient of two polynomials in P of D. So that's kind of a weird way to think about it. So an easier way is just to show you an example. Oh, and it also has this property where the degree of alpha of A is equal to the degree of B plus 1, which is also equal to the norm of alpha, which is equal to alpha conjugate, which for these really nice lattices is always an issue. So, like, for example, one of them is 1, I. The norm of alpha is just 1, which means that this is just a linear in POC over a constant term. So it's just a linear function. So another one of these is, so for L equals 1, square root of -2, we can write the P function as this. P is the square root of -2 times Z equals, now the degree of A is going to be 2, because that's the norm of root negative 2, and the degree of b is going to be 1. So we can write it as a b of c plus d plus 1 over c plus d. Now, and there are lattices for which omega 2 has a much higher norm, and those are the hard ones. But we can get Mathematica, so use Mathematica. We get Mathematica to write this guy out as a series, and we get Mathematica to write this guy out as a series. And so this is some non-complicated thing involving z's and omegas, and this is the same thing. It involves a lot of z's and omegas, but we can compare coefficients. And these G2 and G3, they appear in the series expansion of P of Z. And so if you compare enough coefficients, we get G2 and G3, and that gives us the equation of the curve in terms of x and y, instead of just kind of this weird abstract lattice. So that's basically it. If there are any questions, I'd be happy to. Yeah?
When you use Mathematica,
Yeah.
what did you have to just approximate some errors and to get the coefficients, or?
Yeah, I mean, yeah, you can get them exactly. You solve, like, you can solve for A, B, C, and D for any alpha.
What was it you asked Mathematica? You gave it the lattice and then?
Oh no, I gave it the P function. The Mathematica knows the P function, and it knows how to write power series. And you just expand it out to enough terms. Do the same thing for this thing. It's kind of a pain, but you can do it. And G2 and G3 appear in the power series